Okay, we were on this topic of handling I/O and how that might impose some external constraints on the way we do synthesis. It might translate to some behavior such as some of the operations that we have in our design may be attached to some clock cycles. For other operations you have the flexibility, but some operations are attached. As you can see, that can be handled in an overall methodology by fixing those schedules for some of the operations. For the rest of the operations you still carry out the normal resource constraint or time constrained scheduling and so on, but these implications are there, which may limit some of the flexibilities that the scheduling tool has. For example, the original flexibility we said, which is that any operation can be scheduled anywhere, that might be removed because of these constraints. But let us move on to another very important limitation and what to do about it. This has to do with timing. Let us see what are the timing approximations we have made so far in our formalisms. We did the scheduling problem, we did the binding problem of various kinds, but the register allocation is what we looked at. But it is the scheduling that sometimes has to be refined in some ways because of the timing approximations that were made. What kind of approximations? First of all, in the interest of simplification, we said we first do scheduling and then do function unit binding. This sequence automatically imposes some restrictions of a nature that let us take a look at. So, an FU can perform different operations in different control units. So, here we have done the scheduling and then this FU binding step was taken, which mapped these two additions into the same resource and the other two additions into a different resource. And these were done in sequence. First we did the scheduling step and then we did the binding step. This implies some kind of a muxing structure. The moment you have a sharing of resources, in the general case, this will lead to a mux at the inputs. Why would it lead to a mux? Because the operands may come from different places for that same resource in different clock cycles. Okay. So, in the general case, if I have these two operations scheduled into two different clock cycles, I might have a 2-to-1 mux at the inputs of the adder. This is one of the adders, but for the other adders also I would have a similar sharing. So, mux is implied. Mux is implied means that there is a delay due to the mux, right? There is a combinational delay. And of course, we have to account for that delay. Where do you account for it? What does it affect? If the delay now, the combinational delay that I am concerned about is not limited to my adder delay, but it also has a mux that is connected in sequence, then the real delay of the combinational, this is a combinational path, right. From the mux I have a combinational path leading to the adder. So, the delay would be the sum of these delays here. That much has to fit into the clock period. But remember, what was the assumption we made in the scheduling phase? As we were doing the scheduling, we were just checking whether the operation fit into the clock period or not. We looked at the adder delay and we were checking how much did it measure compared to the clock period. If the delay was more than a clock period, then we would say we will divide and take the ceiling, and that makes an integral number of clock cycles. If it is much less than a clock cycle, then in fact we could accommodate multiple operations into the same clock cycle. Either way, we did not account of this implication of a mux that is the result from the sharing. Why did not we account for it? because we did not know, it is too early during the schedule phase to make that decision. That decision, in fact, sharing decision is being taken later on. So, the MUX is inferred only later on, but that information needs to be provided to the scheduler in order for it to generate a correct schedule. Otherwise, you may have an incorrect schedule, right. If you can easily see that if this delay of the adder was very close to the clock period, then adding the MUX will actually lead it to overflow into the next clock period. So, that is essentially an incorrect design that the scheduler would result in. This is an important restriction, right, but how did it arise and what can we do about it? If we separate out the steps of the synthesis into one scheduling phase, one binding phase, function unit binding phase, that was done in the interest of simplifying the engineering somehow, but that leads to issues of this nature. What could we do about it? We could in some ways combine both the solutions to the scheduling and the function unit binding. It makes the solution a little messier, because if you look at the algorithm for scheduling, it was formulated in some way and it was solved in some way. The problem formulation for FU binding was totally different, and that was solved in a different way. Now, to do them together does complicate the solution. You could do it, but it makes it more complex. You could still retain the structure, the sequential structure of these steps doing scheduling and binding, but we could pass some information or enhance that problem statement in some ways. For example, you assume first there is a fixed MUX that is there at the input of every function unit. Okay, like a 4 to 1 MUX. I do not know as it is, whether it is 4 to 1 or 2 to 1 MUX is realized only much later, but for the purposes of generating a correct schedule, we could assume that the delay of the function unit is not merely the combinational delay within the function unit, but also if you add the MUX at the input. The problem with that is I do not know the width of the MUX. So, let us assume that it is a 4 to 1 MUX, just so that we have a correct design, not necessarily optimal. You can see that this kind of things give up on efficiency and optimality. Nevertheless, correctness is more important, as we have seen earlier. So, let us assume a fixed MUX size. Let us assume that all the function units have such fixed MUXes at all their inputs, so that at least the analysis is easier in some ways. The way to analyze now would be that I just extend the delay of each of the function units and then do the regular scheduling. But this could be an iterative process, because the binding is now constrained. If I say there is a 4 to 1 MUX at the input, now when I go to the binding stage, I should not allow more than 4 paths simultaneously, of course, to the unit. Well, not at any point in time there is only one path, but I should not allow more than 4 connections to the input. If I impose that kind of a constraint, it is possible that you actually do not find a solution. Binding is not able to find a solution. If it does not, then maybe I can increase it, make it 8 to 1 or something like that. Just in the interest of speed, there is no reason why after 4 to 1 you have to go to 8 to 1, but then in the interest of reducing the number of iterations, you could do such a thing. Of course, this process will converge somewhere. If it converges at 8 to 1, you could further try to extend the search, and maybe you find the best solution, which is 6 to 1. You do not need more than a 6 level sharing, but such an iterative process may be needed to get around this, but the important thing is that this approximation is made as we treat scheduling as a different step and function unit binding as a different step, because the results of the scheduling of course need to be correct from a timing point of view.
Sir, isn't the problem same as wiring delay? So that also we assume.
Wiring delay is also an issue, but we will talk about the wiring delay. This is an issue that comes up independent of whether there is a wiring delay. Even if wiring delays are all 0, then too this problem shows up. So, in some ways this is a different problem. That could be solved if you have a tighter integration between the scheduling step and the FU binding step. You do not need to have accurate wire delays, which is a totally different sort of analysis from this kind of an analysis. This solution still works at a high level, you do not need anything more. It is just that there is an interdependence between the two high level steps, but that is a little messy if you want an exact solution. But you could approximate the process by introducing some fixed number of iteration between these two steps.
So in this case, when we increase the mux size, we will increase all the muxes that were there at the end of every function unit.
That is the pessimism we are talking about, because you do not know the sharing until much later. So, you put that mux at the input of every function unit. It is a pessimistic solution. You are trying to get a correct solution first. Later on perhaps you could, so nobody is saying that you stop here with these iterations, because even if you start off with a 4 to 1, that could be a bad solution, because the real sharing degree might only be 2 to 1, right. So, 4 to 1 would give you a correct result, but that is not necessarily the best one. You could iterate further, like you said, we said you could extend the iterative process to find the best muxes. The best mux width may be different at the inputs of the different function units. So, as you can see, if you have a large number of units, each unit actually has 2 inputs and so on, there is a very large number of combinations. Even here, what is the ideal mux width at the input of each of these? This is a sort of a tricky problem. That what at least that introduces is a large number of iterations in the sequential scheduling and function unit binding step. However, this too is not exact. In this assumption that that kind of sharing that I had here for those two adders leads to this sort of a mux, what is the assumption we have made? If the FU is shared in 2 different clock cycles, what would be the extent of the mux width is the question.
I was thinking that we had just considered this particular flow graph.
Yeah, this is for even for this is the example.
Assume assumption like a mux won't be used for any other inputs.
Even for this graph, let us restrict ourselves to just that orange adder, just one adder. We said that this is the implied design. Is this always the implication? Or in other words, is a 2 to 1 mux always inferred from such a schedule and binding decision? Could I have a 3 to 1 mux just for these, for the two-way sharing of the same resource into clock cycles? That is my design. That is not the, yeah, it is a seriously posed question, but that is not a trick question. This is a 2 to 1 mux. Obviously, there are only 2 operations, 2 is the level of sharing. Could you throw out the mux completely for some circumstance? Or even one of those muxes? But in general, the question is, just because a resource has been shared across n operations in the schedule, does it mean that I will have an n to 1 mux at its input? This affects the quality of our exploration, because if I knew that a smaller mux width would be okay, then I should not unnecessarily assume that n to 1 mux. Remember this design methodology, if I say that I fix the mux width, how will I fix the mux width? It could be based on the degree of sharing, right. So, but degree of sharing can be large for the same adder, but does not mean that I need, if 10 different operations widely separated across clock cycles, if they are sharing the same adder, will I need a 10 to 1 mux or not necessarily?
Can I replace it with a register?
Replace what with a register?
Mux.
Can the mux be replaced with a register?
If I have just two registers.
Register we have not even talked about. Registers are involved in the process. Where are they involved?
So
To
if I
store
just need
each-
two
For
registers,
example, to store all these intermediate signals, you do need a register. That should lead to resolving this question of whether I really need a 2 to 1 mux or an n to 1 mux. So, the width of the mux is determined by what?
How many sharing is across how many cycles I will be sharing? So for
Across how
example,
many cycles I have shared the function unit? Yes.
For here, first I am sharing for first cycle and then for second cycle.
Right.
So in first cycle I am giving A and B, and then
Right.
in second cycle I am giving E and F. So let's say there was another level which is third cycle where I was using this mux, then it would have been 3:1. Mux.
Yes. So the generalization is if I have n different uses, I need an n to 1 mux.
So if the same functional unit is used across n cycles.
Yeah, yeah.
then-
So
yes.
that's our
Yes.
our design. The same functional unit is used. That's being shared. So the extent of sharing in the schedule is n. But does that mean that I have an n to 1 mux? Clearly, a max of an n to 1 mux is what I need. But could I do with a smaller width? Or what actually determines the width?
Probably we were looking at lifelines of this register. So how
Right.
many registers we need, right?
Right.
So I'll look at if I have multiple registers which are available across this lifeline where I was sharing my
Right.
muxes, then probably I can reduce it depending upon my register count.
Depending upon, there is a dependence upon the register. What is that dependence?
So if we could have a register coming into the adder,
Yes.
and a register value could be updated
Right.
on time by time, then muxes could be
Could be reduced. So let us clearly identify this. Each of these inputs comes from where? Comes from a register. So if I have 3 or 5 such edges that are coming into that same operation, right? A sometime, E some other time, and so on. Do I need 5 paths in the data path? They all come from registers. So do I need 5 paths from 5 different registers to that mux? I don't. I could do with fewer because
So we can have a memory at the register, we can read only one.
the model here is that every one of these is going into some register. If it is crossing a clock cycle boundary, then it is going into a register. But nobody is telling you that they are all distinct registers. A and E could be assigned to the same register. If that were the case, then that mux would not be needed. So the number of paths you need into a particular function unit, a particular operand of a function unit, depends on not just the degree of sharing, but actually depends on the number of independent distinct paths that are there from different registers. So if some of these inputs are actually mapped to the same register, then you could have a few have a smaller width at the mux.
They will be differentiated based on the clock cycle then.
Right. At our assumption of register allocation, of course, is that in different clock cycles, that the same physical register may store different data. So this is actually an example of that. I have one register, that register could store A in that cycle, and in fact in the other cycle here at the end of the first cycle it could store E. So actually I do not need that mux. If A and E were to map to the same register, same physical register, then in the data path you need only one path from that register, output of that register back into this adder. You do not need multiple registers. That of course complicates the problem further, because register allocation is the third step. Right. So, that is just pointing out that if you want to be really aggressive about determining what the width should be, even the function unit binding step is not good enough. In fact, when you have a large number of operations like 10 or 20, it is very likely that the same register could possibly be sharing multiple of those 10 different operands, and in fact the number of paths might be much lesser than the degree of sharing of the function units.
So when we were using this graph coloring algorithm to solve the register allocation, right?
Yes.
At that point of time we were looking at the lifeline of a particular
Yes.
value,
Yes.
right? So this is what I need to do. So I need to see that. So for example,
Well, what I need to do is solve all the three problems together now. We already said that scheduling and FU binding have to be done together. Now we are saying register allocation also has to be done together for me to really solve this problem and get my MUX widths. So anyway, that is just to point out, but that is reality. The number of paths that is there is not merely the extent to which I am sharing the FUs. It is the number of independent paths that show up. All these inputs are coming from registers in the general case. So it does depend further on the kind of register sharing. So from this you can say that you can see that there is an impact. I could actually use this to influence my register allocation itself. I should share the registers in a way that the number of these paths is minimized, right. In addition to minimizing the registers, that could show up as a further parameter that influences the register allocation. Let us look at the register side. Now, if register allocation follows scheduling and FU binding, we already actually argued that it need not, and you are already giving up some optimality, some efficiency at the timing level by following this sequence. But nevertheless, I have sharing of registers, and the input to a register may come from different function units. What does that imply? That implies that there is a MUX that may be inferred at the input of a register. If I say that F and G are both sharing the same register, then since F is coming from some function unit, this one, G is coming from a different unit, I have a MUX there. Right. For in our design here for E, I did not need a MUX because there was only one value stored in that other register anyway, but for this register I needed a MUX. Now you can see that that MUX also influences the critical path of the design. So, there are two kinds of MUXes. One is the MUX that is inferred here at the inputs of the function units, but the other is this MUX that is due to the register sharing. So, do you see that this also influences our scheduling decision, because now we are saying that I should have enough time for that MUX, that operation and this MUX. All of them could be in sequence, and the combinational path that is formed through that sequence, all of that has to fit into the clock cycle. Again, it is too early. When do we solve this? Clearly it is the scheduler that is taking all these timing decisions and deciding that this should go here, that this operation should go here, the other operation should go there, and in fact the problem is not as simple as that. There are uncertainties here at the inputs of the FU. There is a different level of uncertainty at the input of the register that it also needs to be aware of. Okay. So, in advance the scheduler cannot know the MUX size. What can I do about this? I can integrate now everything if I really want an optimal solution. Actually, nobody is preventing us from that. There are integer linear programming based formalisms for solving the high level synthesis problem, where in theory you can combine all of this into one problem to be solved. Again, ILP cannot be solved optimally, but at least the formulation is there, all the parameters that affect the problem, they are all there. We did not talk about it. Our approach to these problems was a heuristic approach. We took these priority functions and simple approximations, just in the interest of practicality, but it is not as though you can't integrate. You can, it is just that you can first integrate and then adopt some heuristics to solve these. I could iterate otherwise, scheduling, binding and register allocation all in a sequence, but with the same extension that we looked at earlier, like you assume that there is a mux size, fixed mux size during the scheduling, maybe it is 4 to 1. FU binding, register allocation, both of these are constrained. So, register allocation is constrained means that there can be no more than 4 paths to that register. It is a little tricky, it is not as though there are only 4 edges in our data flow graph that should go into the register, because the physical path comes about from individual FUs. Right, it could be that I have the same function unit that is producing different results in different parts of the data flow graph, and those are going into the same register, means that you need only one path, you do not, that does not lead to a mux. So, if I have one unit here, some other unit here, and you decided that this and this, both of them are mapped to the same register R. The question is, does this lead to a mux? For the same reasons as earlier, it does not necessarily lead to a mux, because both of these could be mapped to the same function unit. If they were, then I have this kind of a design. These are different parts of the schedule, I have A and B, but because these two adders are shared, in fact there is only one physical path from the function unit into the register. Right. So, there also we should be careful not to overestimate the number of paths, and therefore, the width of the mux that goes into the register. Okay. So, that is one kind of uncertainty. Of course, there is a classical uncertainty that we have pointed out at different points of the course. In the interest of saving computation, we have actually ignored all the wire delays. Actually, beyond this kind of approximation regarding muxes, there are a couple of other things that happen. One is the function unit delays. What determines the delay of a function unit?
The critical path for the combination logic.
Yeah, so it is implemented in terms of combinational logic, the critical path through that, although we have not formally defined it, but it should be clear that the longest path from any input to any output is the critical path of the design, that determines the delay. If I have an operation of that nature, how do I know what is the delay? Is the delay clear, or there are uncertainties there with respect to how much the delay is? One thing is, the delay of an adder is not specified and is not fixed, it depends on the width of the adder. Right. Of course, a 10-bit adder takes longer amount of time than a 5-bit adder. So, I actually should look at the width of A and B and instantiate that adder that is necessary. There is no need perhaps to instantiate a wider adder. In the general case, that adder may be shared across different function units, and actually we glossed over this during the sharing formalism, but we do have to somehow influence the sharing in a way that we encourage the algorithm to share if the two adders are approximately of the same width. If the operand widths are very different, then it is not worth sharing, right. If for the narrower operand you are wasting this combinational circuit. So, that is there. The delay certainly is a function of the width. How do you know the width? You have to actually look at the now the type definitions of A and B, and you can determine the width. But of course, you have shared that add operation across some different operations. So, you somehow have to account for the max width of all of those operations that have been mapped onto this adder. That is one thing. Other thing is, it is a combinational circuit. Combinational circuits delay depends on what factors? One is intrinsic to that combinational circuit, there is a delay. For example, you just take an AND gate, what does its delay depend on? You can, so it does a one standard cell that you have instantiated. It has been characterized for the longest delay from any of its inputs to any of its outputs, and we say that that is the delay, the max of those paths, internal paths that are there, that constitutes the delay of the gate. But that is only part of the story. Delay depends on other factors. Like what other factors? Number of inputs is known or not known? Yeah, if I tell you it is a 2 input AND gate, then you certainly know this, and in fact it is a one standard cell that has been instantiated. Of course, the standard cell designer has characterized that and has given to us as it has populated the library and it has told us that this is the delay. So, presumably it is the max delay of any of these paths. In general, those paths could have different delays, it depends on the circuit of course, but that has been characterized. It depends on one more thing. Yeah, it is instantiated as part of a bigger design, right? What does it depend on? Ports are available or not? What do you mean ports are available?
We do the ANDing operation.
Yeah.
So if the inputs are not available, like it comes from the other parts in the dependency.
Yeah. This is one of the factors. The rate at which the inputs are rising and falling do contribute to the delay, propagation delay of the gate itself. It does, right? When you characterize this is in terms of you are making some assumption about how sharply the input is rising. If the input instead of rising in this way is actually rising in this way, then of course the delay is longer, right? That is one thing. What on the output side? It is a function of the load. What you are connecting the AND gate to, of course, determines if the load is greater than the delay is greater. So, those are external factors. There is an intrinsic factor regarding what is happening inside your circuit, but the delay most definitely is a function of the fan out of that design. That too is an approximation that we have made so far. We did not care about what it is connected to in computing the delay. This is a little messy, as you can see. This maximum, what is the max load? When the library has been characterized, when the adder has been characterized independently, there was an assumption that was made about the maximum fan out. Right, but did we take care of it in the scheduling, resource allocation, binding? Nothing, right? We did not take care of it. So, in fact, that delay is a complicated equation. It is a function of the width, but it is also a function of what it is connected to, some of which is clearer only in later stages. In the interest of simplifying the steps, we have made assumptions along the way that we somehow have to remove. Generally, that may lead to an iterative solution, which may mean that you make certain assumptions and it may turn out at the end that does not work. When do you know this anyway? At later stages you do know, but anyway one of the approximations is that the fan out was ignored. That is one. And of course, the wire lengths are still unknown. Even at the end, the fan out is still a logical entity. You can count how many gates it is connected to and so on and determine, and based on that you can provide some information. How do you provide that information? You know what it is connected to. At some stage you do know what it is connected to, right? It is connected to this, it is also connected to this, and for these individual cells or whatever it is connected to, after you know these connections, you do know the load that this offers to anything that connects to it. Right, and you can add up all of those capacitance values and that will tell you the load. So, that is at least a better picture, a more refined picture of the load than earlier, but reality of course is that all of this also adds to the load in some way. That is a function of the geometry which is realized much later, which introduces a very fine dependence between all of these high level and logic synthesis levels of abstraction and physical design which takes place later. So, it is the same circular problem that we are talking about, which is ideally it would have been great if we knew what those delays were, but in fact the way the design methodology works, we do not know those delays. Now, you can say that placement and routing should also be part of the scheduling, resource allocation and register allocation and all of these steps. So, in the general case you can see why this methodology is a little messy. There are these weaknesses that are there, which leads in the practical case to an iteration in the design flow. That you make some assumptions, it is not that you throw out all of this just because there are these deficiencies. At various levels you make different assumptions. One of the primary assumptions that is made is that out of the clock period you exclude some fraction of that clock period as not being available to any of these high level steps. Placement and routing often does that. So, you do your timing analysis on the net list, the gate level net list, that is still very approximate, right, because you do not know the geometry of the wires. But the solution around that could be that you leave 25% of the clock cycle for delays to be populated later on when we have further knowledge of the geometry. That is all right, it is not the best solution, but at least it is some solution that helps avoid an infinite loop in the process. There is one final delay related issue that we should be knowing, because we have an idea of the kind of output that high level synthesis is ultimately generating, right. There is this data path. On the data path side there is this, you have registers, you have some muxes, you have function units, you have another bunch of registers. We said that there are these muxes that are inferred at later stages after the scheduling, but this is what the data path looks like, and this is what the FSM looks like. Right, and I put them together in this way that we already saw when we defined the problem itself. So, let us look at it from a timing point of view. Of course, a correct sequential design should finish all its combinational work within a clock period. So, that is my clock period. Let us see what all are the different delay elements that are introduced in this process and which all could possibly form the critical path of the design. There is an FSM, here itself there is some logic, right. You read the state register, depending on which state you are in, you would enable or disable certain function units, you send appropriate select signals to the muxes. So, of course, that does not happen in 0 time, you have to spend some time here to actually generate those signals to the select inputs of the muxes. So, there is some combinational path delay here, we will call that the FSM delay. Actually, even before that there is a flip flop propagation delay. So, at the rising edge of the clock, it takes a while for the whatever is there at the D input of the flip flop to be propagated to Q, right. Then only you can do anything else. The Q value is visible to the combinational logic after a certain propagation delay, that is also not 0, right. Of course, there is some non-zero delay there. So, we start off with that. Then there is an FSM delay, we have to go through that. FSM does control what is going to happen in this cycle. So, I have to do that first before any computation can take place. In fact, to decide which is the path that actually leads to the computation, I have to first do my FSM. So, that does come first. Okay. Then there is this MUX at the input of the FUs that we already saw. Then there is the FU delay. Later on I have the MUX at the input of the register that goes into the register, but as you know the flip flops here are associated with what is called a setup time, right. Before the rising edge of the clock, I should have all my data ready, so that the appropriate setup time that the flip flop needs is satisfied, otherwise you will not latch the input correctly. So, these are the delay elements that I must be aware of in the general case. Some of these are fixed. You can say that the flip flop has been characterized already for its propagation delay and for its setup time. So, that much is fixed. So, if it is fixed, then it is easy, we just subtract that much time from the clock period. Do not make it available to the scheduler. Ultimately, the scheduler needs to know whether I have enough delay available in the clock period or not, but this is not hard to fix. For whatever the clock period for the design is, you subtract the appropriate amounts. So, that is what we are left with. MUX delay, FU delay. So, this part is what we already looked at, right. It is complicated, but some handle we have around that. What about this? FSM delay has to be accounted for and subtracted appropriately from the time that is available for the data path operations. How do I get that?
So FSM is synthesized at a later stage only. So
When does the FSM come in? After scheduling, you know the FSM. That is not all, not the entire FSM. The structure of the FSM you know in terms of the states. But there is something that is not known at the end of scheduling. What is it? The control signals are not known, right. You have a schedule that does result in whatever the paths are, it structurally in a 4-state FSM that looks like this, but states are not everything, right. In the FSM I have states and transitions. In fact, this is a linear FSM, we already know what the transitions are, and in fact, if there are conditionals, then we also know what those conditionals are. So, that part is clear. What about the output part of the FSM? Do I know this at the end of scheduling? I do not know. Why do not I know? What is unknown?
Functional unit binding.
In fact, whether there is a MUX or not is unknown at this time. You do not know whether to select whether to send a select signal to the MUX, because you do not even know that the MUX is going to be inferred. MUX gets inferred later on in the FU binding, register allocation and so on. Until that time, you actually do not know what signal to send from the FSM, right. So, you have a partial FSM at the end of the scheduling, but in fact that is not all. The complete FSM is inferred at the end of all of our steps. The sharing steps are done, and therefore the MUXes are inferred. We know what are the MUXes. Now that we know the MUXes, these MUXes need to have the appropriate select signals, and we can construct the complete FSM at a later stage. But in fact, we want to provide this as an input to the scheduler also. This too has to somehow go through a similar design methodology. So, you could do something smarter with respect to estimating the delay. It is not as though you know nothing, you do know something, and based on what is known here and resource constraints and so on, you could build a model. Actually, we have done some work in this area, where from a high level inputs that are available to the synthesis tool, even at the scheduler level, how do you actually estimate and account for the FSM delay, so that you can appropriately adjust how much time is really available to the scheduler. But it is a very interesting problem to solve. You would like to know all of those delays and account for them as early as possible, but the methodology is such that you can't possibly have all that information. So, hopefully that was clear. What all are the delay elements that affect our clock period? There are other paths. What I have highlighted here is one path, possibly the more important path, but what other paths are there that we should be worried about? Notice that this signal, control signal, is going here, but it is also going here. This one may be a little safe because this is the one that appears early, right. This one in fact this signal may be ready as soon as that signal is also ready. So, does not affect the critical path that much. So, that one might not affect too much, but this one might. But that is not the only path. As you can see, this is one path, that is the path that we talked, but this is also independently a different path, right. Whether the longer path is through the select line or from here directly through the inputs, that is not clear. You have to look at the circuit to see which one is the longer path. If it happens that the path through the function unit is actually longer, then it is all right, then you could actually ignore the FSM completely, but in the general case you do need to worry about this. Okay, let us move on to a few other architectural extensions that we might have as a consequence of some of the other issues that show up. One issue is the impact on the later physical design steps. So, the way we have formulated these problems, these are all discrete registers that get inferred R1, R2, R3, R4. You may have a large number of registers, a large number of function units, and in general there could be a very messy interconnect structure like that, which again we said that we need to do something about this. Awareness of the delays due to those interconnect structure is important for us, but it is hopeless to try and anticipate all the delays at the level that makes a difference, which is during the scheduling. So, we can think of different ways around this. Those ways include restricting the architectural flexibility in some way. We did talk about this when we talked about interconnect. For example, you have introduced some buses and so on to make it a little easier to predict the effect of these things on physical design, easier to predict. Some of those may influence the way we organize our data path elements themselves. One good example is you could actually put together many of these registers into one unit called a register file. If you actually need access to all of them at every clock cycle, then it is a different matter, but there will be a large number of registers. Well, their usage may be not all simultaneous for the most part. Then you could actually group them into a register file kind of an architecture. This is more modular and could be generated automatically in some way through a memory compiler kind of a tool. There is a trade off here. This does help predictability, it does help the physical design part, it helps layout and so on, but what you are giving up in the process is of course the extent of connectivity. There is a limited connectivity. So, it is limited by the number of ports that are there in the register. You could put a large number of registers there, but you might not be able to afford as many ports. The ports might be limited. If ports are limited, then it does go back and influence some of our other steps, because all the data cannot be simultaneously accessed. But the other way to look at it is that such an architectural feature could actually be incorporated into some of our high level synthesis steps. Yeah, these are optimization opportunities that show up when you have a large number of data path elements that need some kind of organization. So, that is one. Let us conclude this discussion with another very interesting topic, something that influences the execution of high level synthesis in a very fundamental way. I have the flexibility to chain operations into the same clock cycle, right. So, this is an adder, this is a maybe it is a copy, it is of the same adder, but we are introducing both of them into the same clock cycle just because there is enough time. Now, how do you implement this? We already saw that the way to implement this is just have the output of one adder feed as the input to the next adder. So, that is clear, but question I want to pose is, what is the max delay through this structure? And there is a big hint there that tells you what the expected answer is not.
It must include the setup time for this second adder.
There are these other effects that we looked at, setup time. There is of course the assumption here that wire delays are 0 and so on, but this is an orthogonal problem. All of those are there. Independent of that, just from a logical point of view, from the combinational logic's critical path point of view, the question can be separately answered. What is the maximum delay you expect through this structure? To help you interpret the question and to indicate that there is no trick or something here. What I mean, of course, is that 20 nanoseconds of course are enough to realize this, but could it be less than that, even though the path that is defined through each of these individual structures is 10 nanoseconds.
If I know that second input is 0 or something.
If you know that
So
the
second adder input is redundant, but that will not be case. That is something which
you
you
don't know that in general. We are talking about, this is a circuit question that is being asked. There is nothing funny that is going on here. You can see what is the general question. This is a specific instance, but the general question should not be hard to answer. You are stuck at the 20 nanosecond here because we have used this example all along, and you are wondering where did we go wrong. We actually didn't go wrong anyway, but let us say I have some piece of combinational logic. This is combinational logic, right? Adder is a combinational logic, and I have some other piece of combinational logic, right? There are inputs here that are passed on to the cascaded input. For simplicity here, we have assumed that it is another copy of the same design. In general, these are the same or are not the same. It is all right. Our argument can be the same, and there are a bunch of outputs. Let me put 4 in. That is my design. So, if I know that the delay through this is 10, if I know that the delay through this is 10, what is the delay through this whole structure? Is it necessarily 10 plus 10? Upper bound is 20, great, but but as I said, I am not challenging your arithmetic abilities. This is computer arithmetic abilities that we are talking about.
So there is no dead logic, right?
There is no dead logic. If it was dead, I would throw it out of it. This is a library element. Somebody, a respectable designer, has designed it, and of course, he has not filled it with blank space or some such thing. So I am taking an off-the-shelf component, which is an adder, and I am cascading these two. But in general, this is a function, and 2 functions I have cascaded. I am asking the delay through the combined cascaded structure.
So this 10 nanosecond is the maximum delay which is given by the person who has characterized.
Who has
this.
characterized it. So there is no reason to disbelieve him once he has said that.
Sir, the 10 nanosecond is the worst case delay for the critical path.
Yes. Yeah.
So
That by definition, it is the worst
if
case.
we are not using the critical path, then we can complete in less than that time.
Okay. So tell me what should.
I mean, this is the 10 nanosecond is the worst case scenario. We can have a best case scenario in which we can complete the operation in less than 10 nanoseconds, and then the second the combination logic will get the output.
Oh, so are you saying that for some operands, for some data values, you will get the result in less than 20 nanoseconds? But that's all right. But this bigger unit now needs to be characterized, right? This is now your design. You have to characterize it when you sell this to a customer, and the characterization cannot be that for some particular combinations of data that I am not going to tell you, the delay is much longer. That is not acceptable. Indeed, it is worst case, that is an understood thing, but question is, if 10 is the worst case for this guy, 10 is the worst case for this guy, what is the worst case for this? That is not to say that this argument has no merit. If you could show that the worst case that could come here cannot also occur simultaneously here because of the nature of the logic, then you could argue that my worst case for this combined structure theoretically never leads to both the delays being 10 nanoseconds. If you could argue that, then it is it's fine. Independently, that is a different analysis, but my question here was more from a structural point of view. But the arguments are similar. This has to do with the with this general observation that if you have two cascaded elements, you have worst case of one, worst case of the other. The worst case of the cascaded unit together is not the sum of the worst cases. It is always, almost always pessimistic. But you can see that in this example, it is in this simple example, not yet in that adder example, because there we did not go into the detail, but this example you can see give a general worst case path for this function unit.
One perspective which I can think of is that, okay, I had cascaded same design, same component, right? So for the first output to appear, the delay is like the whole cascaded path, but then once the outputs are available, the rate, so it's more of like pipeline effect can be seen.
That is a different kind of an architectural element. There is no pipeline here because this is a of course this is a combinational circuit. You are getting closer and closer to what I would ideally like to extract from you and not want to just pose the just give up.
Combination block is executing, the second one can use that same time for setting up its input.
You are absolutely right, but I want you to complete the argument. But this theoretical argument can be easily completed. I said that the worst case path in this element is 10. Given a generic, how many paths are there in this design from any input to any input to any output? How many paths are there? Which could be possible candidates for the critical path? Is that also something that needs analysis? There are 4 inputs and there are 4 outputs. How many paths are there? It's a black box, so any of those could be the critical path, right? So there are 16 paths, and just let's identify. Give me some path that could be in general the critical path. Like this. This is actually not bad. From adder works like this, right? The least significant full adder influences ultimately the carry out or the sum of the MSB sum, and therefore that could well be it. In this other design, similarly, that's the critical path is the same adder, right? Does that tell you what that is you are severely overestimating the delays by adding them up? Where is the critical path of the combined circuit?
Most of the time will be overlapped. I mean, after the first bit is calculated, when the second
Right.
bit of the
second adder can begin adding as soon as the first output, the sum bit, is available.
it is little more than the worst.
It is marginally higher than a single adder. It does depend on the architecture, but at that level of abstraction where we drew this adder design, it seems as though there is no argument. But if you look at the implementation of a ripple carry adder, this is what the circuit is likely to be. This is the first addition, this is the second adder. Result of one, that is the sum bit, these are the sum bits, right? Those bits are going as inputs to the second adder. Critical path of the first adder is this. Critical path of the second adder is this. Critical path through the whole circuit is not the sum of the critical paths. That would have been only if there was a path from here back to there. Therefore, in fact, for a ripple carry adder kind of a cascaded circuit, you can easily see what the equation is for the critical path of the cascaded design. So, if each were 2, there is a full adder delay. That full adder delay is any input to any output. Here too there is an approximation, because that input might be this delay might be different from this delay. And in fact, what when we talk about critical path, we are worrying about the in general the carry in to carry out delay. That is the one that needs to be optimized. Actually, if you look at some of these smarter adder designs, they try to make sure that the carry in to carry out is what is optimized. The data to sum, that path you do have time for, that is not on the critical path of a wide adder, but it is the C in to C out which is on the critical path.
So ultimately, analysis is that we have broken down our operation, which was of 10 nanoseconds, into multiple independent operations, right?
Yeah, in the analysis, as part of the analysis.
So it's more of like a pipelining kind of effect.
But how can this
So,
be generalized? I mean, we could easily
if-
have a architecture in which the most significant bit was the
Yeah.
first input.
Yes, yeah, that is the
Yes.
of course the reason it shows up as a problem is this. It may not be as easy. You can see in the ripple carry adder case, if this delay, the delay of one adder was 6n, where n is the full adder delay, then the delay of the ripple carry structure of the cascaded structure is not 5n, it is 6n. Right, that is all that is there. But this is simple only for this kind of a structure. Okay, so 2 implications. One is that this knowledge leads to much tighter schedules. Right, you could actually cascade a number of additions all in the same clock cycle. So 10 plus 10 was way pessimistic. You do not have to do that. And of course, these principles are exploited nicely in alternative adder structures like carry save adders that people use. But so this is one thing that is of course something that you would like to do. This is nothing new. These ideas are well known to designers, and if a high level synthesis tool has to work well, has to produce good designs, it has to anticipate things like this. Otherwise the circuits will not be acceptable, the delays will be way too much. So if you are aware, then the schedules can be much more efficient, of course, but this is also a little difficult problem. It leads to a lot more work in general for the scheduler, because the units that are being cascaded could be anything. These were simple units, but it could be that well, if you had carry look ahead adders instead, you would need a different analysis. If well, there are 5 elements that are being changed, one is a multiplier, one is some other unit. In general case, this does lead to a lot of computation. How do you do that? It could be that you could build statically a table that says if this unit is cascaded with this unit, then the result is this. Okay, and the number of units in the library is small, so hopefully the table is small. Okay, but this is just the starting point. Second thing is that you have 10 different kinds of units. It is not as though the chaining is only two-way, right? You may be chaining 3 units or 5 units, and then that table does get larger. Not just that, now if I begin to say that I have a 4-bit adder or a 12-bit adder or a 32-bit adder, again this is a function of time. So it might not be a neat function of n, where n is the bit width, because you are dealing with different kinds of operations, you are cascading different kinds of operations. A closed form solution might not be there, closed form expression might not be there for computing the delays. However, designers are aware of such things. So, to match the quality, synthesis tools might often synthesize a sub circuit consisting of those cascaded units as part of a high level synthesis step. How optimal it is, it is a different matter. You cannot afford those kind of times that an RTL designer has when he submits an RTL design to a synthesis, RTL synthesis tool, but even a behavioral synthesis tool, in order to do a really good aggressive design with respect to timing, might as part of, as a subroutine, actually invoke some RTL synthesis tool, or well, essentially it is a timing analysis that is being performed. So, circuits are these components are first instantiated and a timing analysis is being performed as part of an internal synthesis procedure. This is very expensive, as you can see, and often is a step that leads to significantly increased execution times of the behavioral synthesis tools. On one hand, these principles are not new, these are known to the designer. So, if you are aware, if you understand design, then you expect good quality designs. You expect that the synthesis tool should recognize that and give you designs like that. But it is not so easily integrable nicely into our formalisms. Those chaining as an extension to the basic scheduling was introduced as a step that is not so difficult, right. Theoretically it is still not so difficult. We remember how were we deciding upon chaining? We were just saying, is there enough time, slack time left in the clock period, considering what the dependent operations were, the predecessors were, and if there was enough time we would insert it. But this question of is there enough time is a lot trickier. It is not so easy to find out. You may in the general case have to build that circuit and perform timing analysis on that to determine is there enough time or not. Okay. Let us stop here. This concludes the high level synthesis discussion. We will move on to little lower level of abstraction, RTL and logic synthesis in later classes.